Hey everyone, this is David Hilster. I am Dissident Science. Many of you know from my scribers. Welcome. Today we have a great program for you today with Dr. James Maxlow. He's going to be talking again about expansion tectonics. This is his second in a series of a lecture of four. So I want to welcome everybody, and I will start out by showing you some what we're all about, because a lot of people don't. Hey, what's going on, David? I'll just let my slides speak for themselves here. So today is our Saturday Science Chats. We've been doing this actually since 2008. And I want to welcome everybody again from the Dissident Science channel that I have on YouTube, over 3,400 subscribers. Thank you so much for subscribing. And all those subscribers also to our John Chappell, which is getting closer to 1,000 subscribers. I want to thank everybody for their patience. And if you like this, remember to click on the subscribe button and click on that little bell, and you will be alerted to when our next video is going to drop, or our live session. So again, this is sponsored by the John Chappell Natural Philosophy Society and Dissident Science. And the CNPS, or the Chappell Natural Philosophy Society's mission, is to be an organization that above all promotes critical thinking without malice, to be an organization that supports, publishes, and promotes serious scientific work outside mainstream science, and to provide a forum for the open debate about modern topics in physics, cosmology, philosophy, and mathematics, to provide a forum for presenting serious papers and theories without fear of censorship, and of course to be run and controlled in its entirety by its paid memberships, including the elections of directors, and by its members. And again, if you want to join in, we have our brand new website, which is really cool, which is naturalphilosophy.org. You can go there. We've got a brand new website. In fact, we're up to 43 people. We have hundreds of members around the world, but we're just slowly getting ourselves into the new website, which you must re-register. If you are a longtime CNPS member or NPA member, please, you still got to sign up for the new website, because it's a whole different system called Buddy Boss, which is something we purchased the license for, and it is great because you can see everybody. You can go to the activity feed and see what people are arguing about in all kinds of areas, including expansion tectonics, ether theory, people's own particular theories, structures, etc. So you don't want to miss out on that. You can go to that by going to naturalphilosophy.org. And how you can participate, of course, you can sign up at naturalphilosophy.org. It's open to anybody to sign up. You can consider becoming a member. Memberships are annual, and they do help pay. We have about a couple $1,000s a year that we have in expenses, really just for online stuff, including this StreamYard service, which is really great. We also have other things we subscribe to, software. We have our server to pay for. We use Overleaf, which is what we publish our proceedings on, and we publish books through. So your support is very welcome, and it's as little as $35 a year, all the way up to people who if you have some more money and can help us out, that is great, because it goes all toward this organization. No one gets paid. Participate in the community discussions on our website. There are really some great discussions there. If you have any questions, you can go there. In fact, we have one for expansion tectonics, and I saw James finally signed up for our website. Believe it or not, he's more with it than I thought when it comes to technology. So he'll be there, and you can ask the man of expansion tectonics any questions or any discussions you'd like to have. He'll be watching that. And of course, you can post news and happenings about us on social media. Our websites are, the community is at naturalphilosophy.org. Our online magazine, if you haven't checked it out, is at sciencewoke.org. That's for people who don't want to get so much technical and want to figure out what's wrong. You guys are saying something's wrong with mainstream science. Tell me about that. I want to know more about it. You can go there. So it's really made for the layman, but it's an online magazine for critical thinkers. We also have our Wikipedia, wiki.naturalphilosophy.org. And like I said before, Dr. James Maxlow wrote a very extensive Wikipedia entry for expansion tectonics, which should be in the real Wikipedia. But as we know, Wikipedia stands for consensus, which means if you don't put anything that's the consensus, because that's what's true now, then you will be considered either pseudo science and be kicked out. So we have our own Wikipedia. And no, it's not open. Because if it were, people would come in and say anybody's different ideas are not allowed. So it's a closed wiki. If you are a person working outside the mainstream and you want to be included in it with your biography, you can put down all your work. We don't care. We don't care if you have a degree. We don't care what. We care about what you say and the science that you're talking about. Then, of course, coming soon, and we already got people lined up to start to make courses, is the Chappell University, courses in natural philosophy. And our guest today has agreed that's going to be his next thing. And we have professional, it's called LearnDash, learndash.com. We subscribe to that. You have to pay a subscription every year. It's on our website already. And if you are interested even in teaching a course or talking about something and teaching people about some aspect of science outside the mainstream, you are welcome. If you have your own theory, your own model, you can make a course in it so that people can go and maybe instead of reading a book about it, you can actually teach them as if they were going to come to a class. How cool is that? Everything's online the way it is now. It is today and age. So, as I always do, I'm going to put some of my commentary. This is one of the privileges of being the host and abusing your position to say a few things. But as you know, as my dissident science subscribers know, I try to give people the truth about things in science, and it's not always pretty or acceptable. So why do we support everyone? That's one of the questions I get. In fact, some of the old timers from the MPA and the CMPS go, Dave, you and I agree that we should support each other, but you support everybody, even crazy ideas. Well, guess what? There isn't only one accepted model out there. So the answer is because universities do not do this. If you want to go into a university in Australia and say, I'm going to write my doctoral thesis on expansion tectonics, good luck and trying to get that across and accepted by your university. So universities do not listen to people with different ideas, and the same goes with mainstream science. And of course, the change comes from dissent. Dissent is where we move something forward. Something doesn't work. We have this idea now that you can't throw out bad ideas and give you better ones. You have to sort of build upon something that was there. Well, expansion tectonics sort of does that, but again, it comes from the outside, somebody like Dr. James Maxlow. And it doesn't come from groupthink. That's one of the things you learn when you go. It's like someone, Dave, why don't you get a degree in physics and show Einstein's wrong because we have a lot of evidence for that. Well, they're not going to let me. You can't get a degree. So, and then they require you to have a degree. And what happens? A degree means you've gone to the university, have been indoctrinated in what they say is truth, and they don't give you any leeway to say, I don't agree with that. The CMPS, we give a platform, and we are not from groupthink. So that's why we do this, because universities shouldn't. And of course, in the end, these again are my conclusions after many decades of thinking about these things and putting them sort of in sound bites. History decides what's true, not individuals. So if you are watching today and you think expansion tectonics is just the craziest, weirdest idea that the Earth is expanding, or even growing in mass, that's crazy. Well, guess what? You don't get to decide whether or not this idea is right or wrong. That's the beauty. And the thing is that it's not the universities or science evangelists or journalists or even you. It is history is going to tell. So, well, what does that leave us? What do we do? Well, a wonderful person. I love this guy. He is one of the few physicists. He's from Germany, the place where Einstein's from, and he is a critical thinker. And he wrote if you haven't read him, look anything up on Dr. Alexander Unsker. He wrote the Higgs fake, where he talks about the shenanigans going on at the Large Hadron Collider. It's a great book. If you are a science person, you like physics, everyone should read the Higgs fake, so you know how bad the science is behind particle accelerators, and you can get an idea that something's going wrong. Well, what did he say in a number of his talks to our organization during our conferences? He says, keep on working on your passion. That is, if you are passionate about an idea, work on it. Don't care what anybody else thinks. The good news is you can tell us here. We had a guy last week, Alex, and he talked about, was it Alex? I think it was. I've got too many Alexes. But anyways, look at the person who talked last week. Oh, man, I'm getting bad with names. And he talked about these balls that made up the universe and how that kind of model could really work. Well, we're here to support it. It's serious work. The guy's worked on it a long time, and you don't have to agree with it. It doesn't even have to be history that will eventually choose it. But if we don't give a forum and encourage people to follow their passions about what they're doing in their universe, what they are creating in their mind, in their own models or in their own thinking about the universe, then that's not good. We need to support it, and that's what this organization is about. And what we want to do is give a forum to it. So that's why we do it. I'm not here because I'm presenting this because Dave DeHilster agrees with everything that's being said today, the next day, or whatever. It doesn't matter. What we have to do is give ourselves the forum to allow these things to compete and let history decide. But I will tell you today, of course, that's the end of my commentary, by the way. I think this is helpful because, again, I've been around this a long time, and there's a lot of questions, and people don't know answers. And people come, hey, Dave, I liked your answer. And last time somebody asked me about, hey, why do we accept everything? I says, well, that's the reason science is using those words. So hopefully that's something you can do and you can take away with you. So today, of course, you came to listen to it, not to me rattle on, and there are probably some people says, okay, Dave, shut up already. Anyways, we're going to be hearing today a second in a series of 4 lectures on expansion tectonics with Dr. James Maxlow. Of course, if you don't know who he is a retired professional geologist who has worked as a mining and exploration geologist throughout much of Australia. During that time, he returned to Curtin University of Technology in Perth, Western Australia, to study and research expansion tectonics, which, by the way, he coined the word to be different from plate tectonics. From this research, he gained a Master of Science degree in 1995, followed by a PhD in 2002. And there's him smiling. He's a little young. He looks still pretty good, I think. But if you haven't read the book, Beyond Plate Tectonics, Beyond Plate Tectonics signposts that this is something more advanced than basic academic courses might cover, while the subtle subtitle of Unsettling Settled Science confirms our suspicions. The whole book is all revolutionary and new, unsettling to anyone who thinks there will be no major revisions in the earth sciences. It is just as stimulating to those people who understand that scientific discovery will never be finished. And I will say to you, and before I bring James on, and this is my opinion, and I have said this many times, he is not only the greatest living geologist, I think he is really the greatest geologist of all time, because he has been brave enough to put together all of these great men's works together with his own thoughts and take it to where it need be, and do this with no support of any university. But you should buy this book. It should be required that not only geologists read it, but scientists read it, because it affects so many things. And so without further ado, I am going to bring him up, and there he is, Dr. James Maxlow. How are you?
Hello, David. Thanks for that. I'm getting a fat head here.
Oh, very good. Good. Well, you know what I say to everybody is that what we do in our organization is recognize people. I mean, I don't know. Do you know who Halton Arp was? He was
I heard of it, yes.
Yes, he was the guy who got kicked out of astronomy of a telescope because he was looking at peculiar galaxies, and he had the gall to give evidence against the Big Bang. And he sort of died, I don't know, maybe about 10 years ago, but we gave him a Lifetime Achievement Award. And what I always say to people is, even though the world isn't necessarily paying attention now, but will in the future, we represent the future world, and we recognize your talent and what you've given to it. And I'm just super happy to be involved with these people. Maybe my grandkids are going to say, "Hey, my dad hung out with all these important people. How about your dad?" Not too important, but but anyways, I'm going to let you go. I'm going to put you up here with your slides and give us a talk, and I'll hand over.
Thanks, David. Hello, everyone, and welcome to my second of 4 podcasts on expansion tectonics. As previously mentioned, the intention of these podcasts is to look beyond the achievements of conventional plate tectonics in order to show you a uniquely different way of physically modeling the Earth's ancient crustal plates back in time. This modeling uses modern geological mapping of the oceans and continents in order to constrain plate assemblage and Earth's ancient radius back in time. In this presentation, I will be extending on my previous podcast by focusing on modeling continental crusts in order to create spherical scale models of the ancient Earth extending from the Permian back to the early Archaean, about 250 million years ago to 4,000 million years ago. It is once again important to appreciate that what I will be presenting here is a data modeling exercise, not a theory modeling exercise. In other words, all I have done is model readily available geological mapping and global observational data without constraining the data to a preconceived theory. This research represents the first time that continental geology has been used to constrain plate assemblage during the pre-Permian times, and in particular during the pre-Cambrian. This crustal assemblage contrasts strongly with conventional plate tectonics, where heavy reliance is placed on paleomagnetic apparent polar wander studies to constrain assemblage with multiple plate fit options available. It is also important to appreciate that, similar to my previous plate assemblages using seafloor geology, in all cases, with expansion tectonics, there is only one plate fit option available during assemblage. The outcomes of this modeling study are therefore considered unique. This study is summarized in the first 3 models from the left, shown here, shown on screen, and for context, I will also animate the entire history of the Earth extending from the Archaean to 5 million years into the future. A quick digression to highlight current supercontinental assemblages using conventional wisdom. Shown here are the various published assemblages for the Precambrian Rhodinian supercontinent, which is based on the presumption that plate motion across the face of the Earth is a random process, whereby supercontinents break up, collide, and reassemble in a roughly cyclical timeframe. These multiple plate assemblage options are governed entirely by paleomagnetic apparent polar wander paths generated by the various authors, and the multitude of assemblages are literally at the whim of each author. The point I am emphasizing here is that to assemble all of these randomly generated continental fragments on a smaller radius Earth should, in theory, be an impossible task. So let us see what the modern geological mapping enables us to do. The geological modeling study presented here is based on the Geological Map of the World, as first published by the Commission for the Geological Map of the World and UNESCO in 1990, shown here in moleweed projection. This map is based on a global program of continental geological mapping, along with seafloor magnetic and bathymetric mapping, accompanied by age dating carried out throughout all of the oceans and continents during the 1950s to late 1980s. The colors shown on this map represent what I call time-dependent geology, where the colored seafloor stripes, for example, represent the preserved growth history of each of the modern plates. The ages of each colored seafloor stripe coincide with the major geological epochs, extending from the pink Pleistocene stripe located along the mid-ocean ridges, shown here, here, and here, to the the blue Jurassic stripes generally located adjacent to the continents, shown here and here, for example. For the continental crusts, the colours within each of the continents represent bedrock that was formed during the major geological periods and eras. These continental colours coincide with the distribution of the most ancient cratons, shown as pinks and reds, for example in Africa, ancient origins, shown here in South America as khaki, and Paleozoic sedimentary basins, shown as browns, blues, and yellows, for example here in Western North America. By modelling back in time to the late Permian period, about 250 million years ago, it was shown that by progressively removing all young seafloor volcanic crust, plus most of the marine sediments deposited along the continental shelves, all remaining continental crusts unite precisely with a single unique plate fit to form a global Pangean supercontinent during the late Permian period, at around 50% of the present Earth radius. During this seafloor crustal modelling exercise, large Panthalassa, Tethys, and Iapetus oceans were not required. These oceans were instead replaced by lesser continental Panthalassa, Iapetus, and Tethys seas, which represent precursors to the modern Pacific and Atlantic oceans, as well as ancient sedimentary basins located on many of the present-day continents. The preliminary conclusions drawn from these seafloor small Earth models is that there is no requirement for random, non-predictable, multiple plate fit assemblage options or ill-defined plate histories to assemble the crustal plates back in time. Nor is there a requirement for extensive, largely hypothetical, ancient oceans to comply with a constant surface area premise, or for the fragmentation of any of the modern continents to comply with paleomagnetic apparent polar wander studies. Instead, it was shown that the modern continental crusts tightly wrap around and fully enclose an ancient smaller radius Earth with a high degree of accuracy. These continental crusts then assemble against continents that were otherwise not previously considered to be related on conventional assemblages, which in turn presents a multitude of new opportunities to study global data distributions. From the seafloor geology modelling study, small Earth models show that the ancient supercontinents existed as a complete continental crustal shell, encompassing the entire Earth during pre-Permian times at a much reduced Earth radius. During pre-Permian times, continental crust covered the entire Earth, and exposed supercontinental lands were defined by a superimposed network of continental seas, which seas coinciding with a network of sedimentary basins. These seas are not shown on this animation. Construction of small Earth models back to the early Archaean involves a radical approach to reverse engineering geology back in time. This approach focuses primarily on the established network of continental sedimentary basins surrounding each of the ancient cratonic and orogenic crusts. Modelling back in time involves the progressive removal of all young continental basin sediments and intruded magmatic rocks, and simply returning these rocks back to the ancient lands or back to the mantle where they came from. Each continental basin and igneous complex is then restored to a pre-extension or pre-intrusion configuration on a smaller radius model. By moving back in time, the adjacent margins of each sedimentary basin or igneous complex are then progressively moved closer together, while still preserving the spatial integrity of adjacent, more ancient cratonic or orogenic crusts. When moving forward in time, all crustal elements making up the ancient supercontinents and seas are then shown to retain an intimate relationship throughout history. This intimate relationship lasted until crustal breakup was initiated during the late Permian, approximately 250 million years ago, and the modern oceans began to open. From this continental crustal small Earth modelling study, it is shown that the origin and changing configuration of the supercontinents during these times involved a progressive evolutionary crustal process during a prolonged period of crustal stretching, along with changes to both Earth surface area and surface curvature through time. By removing all basin sediments and magmatic rocks, as well as progressively reducing the surface areas of the sedimentary basins in turn, an ancient primordial small Earth with a radius of approximately 27% of the present Earth radius was achieved during the early Archaean, much the same size as the present-day Moon. It should be noted that geological mapping of all ancient cratonic and orogenic crusts throughout the world consistently show that between 10 to 40 kilometres vertical thickness has been eroded from these ancient crusts, which in time were subsequently deposited to form the surrounding sedimentary basins. By reversing this geological erosion process back in time, the sediments are then restored back to the ancient lands consistent with methodologies adopted here. The primordial Earth shown on this animation comprises an assemblage of the most ancient Archaean cratons and Proterozoic orogenic basement rocks. All other rocks, minerals, and elements were simply returned to their places of origin, albeit 40 kilometres thicker than what is shown here. By modelling the surface area mapping data, the increase in Earth radius during the Precambrian times is calculated to be microns increase per year, and the model shown here represents the first 2.5 billion years of Earth history. It is considered from this study that to simply reverse engineer geology back in time and have the most ancient cratonic and orogenic crusts assemble with such a high degree of accuracy, this is further definitive proof that an increasing radius Earth is indeed a viable tectonic option. It is significant to reiterate that on small Earth models, each of the established Precambrian and Paleozoic sedimentary basin settings merge together to form a global network on a common pan-global continental crust. Studies show that the sedimentary basins from each of the continents also coincide with a global network of crustal weakness, operating throughout Precambrian and Paleozoic times. It was within this network of global crustal weakness that crustal extension, generated during ongoing increase in Earth radius and surface area, was focused, as well as ongoing crustal mobility, mantle-derived heat flow, magmatic and metallogenic activity, followed by crustal rupture, continental breakup, and eventual opening of each of the modern oceans. The merging of each of these crustal settings back in time shows that all global crustal-related processes correlate precisely with the overall development of the continental crusts. What the full range of Archaean to present-day small Earth models also demonstrate is that rather than being a random, arbitrary dispersal amalgamation crustal forming process, as we are currently led to believe, crustal development on an increasing radius Earth is once again shown to be a simple, evolving, and predictable process. Applying this small Earth modelling evidence to paleomagnetics shows that all ancient magnetic poles continue to cluster as unique, diametrically opposed north and south poles, as they should. And similarly, plotted paleolatitude measurements coincide with and quantify the location of predicted equator and climate zones on each small Earth model constructed. Additional geographical and biogeographical information aptly quantify the location of these ancient magnetic poles, equators, and climate zones, as determined from unconstrained paleomagnetic pole and latitude data. As will be shown in my next podcast, when published coastal geography is plotted on each of these small Earth models, this geography defines the presence of more restricted continental Panthalassa, Iapetus, and Tethys seas, which represent precursors to the modern Pacific and Atlantic Oceans and emergent Eurasian continents, respectively. From this coastal geography, the coastal outlines and emergent land surfaces on each small Earth model is then shown to accurately define the location and extent of the ancient Rodinia, Gondwana, and Pangaea supercontinents and smaller subcontinents. To once again preempt your question regarding where does all the new matter come from, I will again elaborate on a proposed causal mechanism, as first proposed by John Eichler and outlined further in my book and website. The Earth can be considered a very large spherical magnet, which attracts charged particles circulating in the solar wind. Modern space technology and research has highlighted the input of solar wind-related charged electrons and protons into the Earth. It is considered here that we must at least ask the question and seriously take note of what happens to these charged solar particles, the very building blocks of all matter on Earth, once they enter the Earth. On an increasing mass and radius Earth, it is envisaged that magnetically charged electrons and protons primarily enter the Earth's lower terrestrial layers at the polar auroral zones. These magnetically charged electrons and proton ions are further attracted by conduction to the strongly magnetic core mantle region of the Earth. The elevated core mantle temperatures and pressures present enable the ions to recombine via nucleosynthesis as new matter within the upper core and lower mantle regions. New matter formation requires not only pure energy, but the presence of both electrons and protons, each of which are in abundance. The combination of elevated core mantle temperatures and the abundance of incoming charged electrons and protons within this region may then provide a viable mechanism to continuously synthesize new matter within the Earth. It is further envisaged that new matter synthesis occurs mainly within the reactive upper core to D region of the lower mantle, which in turn results in an increase in Earth mass, this region here. In addition to an increase in mass, this growth of new matter causes the mantle to increase in volume, highlighted by these arrows. It is envisaged that this increase in volume is currently manifested at the Earth's surface by two primary mechanisms. Firstly, as laterally directed crustal extension, which is currently occurring as extension focused along the full length of the mid-ocean ridge spreading zones. And secondly, as an increase in Earth's surface area manifested initially within continental sedimentary basins and currently within each of the oceans. Extension within the upper mantle and surface crustal regions is highlighted in this figure by the paired red arrows shown at each mid-ocean ridge spreading zone, these ones here. This mantle and crustal extension process enables newly formed magma to be squeezed from deep within the Earth, where it travels by convective flow up to the surface, as indicated by the upward-facing magenta-coloured arrows, these ones here. The surface expression of this magma and associated high heat flow process is focused along the full length of the centrally located mid-ocean ridge spreading zones, as well as leakage along known hotspots, volcanic centres, and large and small igneous provinces. Extension within the mid-ocean ridge zones is further accompanied by intrusion of mantle-derived basaltic lava, along with expulsion of new water and atmospheric gases. This lava, in turn, increases the surface area of all of the modern oceans in strict accordance with the seafloor mapping shown in the geological map of the world and small Earth models presented here. In summary, it is concluded that the extensive geological mapping evidence and empirical modelling studies presented in this research more than adequately demonstrate that an increasing radius Earth, extending from the early Archaean to the present day, is a viable and demonstrable tectonic process. Quantification of an increasing radius Earth process back to the early Archaean required an extension of the fundamental cumulative seafloor crustal premise to include continental crusts. Continental crust was reconstructed on pre-Triassic small Earth models by considering the primary crustal elements, cratons, origins, and basins. In order to construct small Earth models, consideration was given to an increase in Earth's surface area occurring as a result of crustal stretching and extension within an established network of continental sedimentary basins. Moving back in time, this crustal extension was progressively restored to a pre-extension, pre-stretching, or pre-rift configuration by simply removing young sedimentary and intruded magmatic rocks and reducing the surface areas of each of the sedimentary basins in turn, consistent with the empirical data shown on the geological map of the world. During this process, the spatial integrity of all existing ancient cratons and origins was retained until restoration to a pre-orogenic configuration was required. By removing all basin sediments and magmatic rocks, as well as progressively reducing the surface areas of the sedimentary basins in turn, an ancient primordial small Earth with a radius of approximately 27% of the present Earth radius was achieved during the early Archean, much the same size as the present-day Moon. This primordial Earth comprised an assemblage of the most ancient Archean cratons and Proterozoic basement rocks. All other rocks, minerals, and elements were simply returned to their places of origin. It is significant to reiterate that on small Earth models, each of the established Precambrian and Paleozoic sedimentary basin settings merged together to form a global network on a common pan-global continental crust. This unique assemblage of all continental and seafloor crustal fragments on small Earth models demonstrates that an increasing radius Earth, extending back 4,000 million years to the beginning of Earth's geological past, is indeed viable. What the full range of Archean to present-day small Earth models also demonstrate is that rather than being a random, arbitrary amalgamation, dispersal, amalgamation, cyclical crustal forming process, as we are currently led to believe, crustal development on an increasing radius Earth model is instead shown to be a simple, evolving, and predictable crustal process. In this context, we should then at least consider that modern global plate tectonic observational data may well be better suited to an increasing radius Earth scenario before continuing to unscientifically reject this proposal out of hand. In my next two podcasts, I will use these small Earth models as a platform to drape additional global observational data in order to further quantify the outcomes of this modeling exercise. Thank you for your interest in expansion tectonics, and for those seeking more information, please visit my website or contact me at my email address shown on screen. Thank you very much.
Well, thank you. Oh my gosh. You can hear me?
I can.
Wow. I mean, this is what you did today. It took me a while to figure out. I mean, it really, and I don't mean that because I wasn't understanding. It took me a while to understand because when I first saw expansion tectonics, I saw it via the animations of Neil Adams. But what he did is he only did the part from the breakup of the continents.
That's correct.
And then if you could do me a favor, go back to the Seafloor Bed, the famous, because I do want to point something out that really made me, I'm going to try to maybe in layman's terms show some of the people
That
watching.
one?
Yeah, that one, that's fine. One of the things that I didn't understand, fact, in the ball that I got, which is going to be, I'm going to hand down for generations. So when we're all gone, my great grand people can sell this and buy an island somewhere. So, but the thing that I notice about this, if you look at this map, which is really the part that he talked about today, is everyone concentrates on the seafloor bed, right? They don't look at what's on the crust. And once you bring it all back, it's sort of, you can see easily by the animations from, Neil Adams and even your stuff, you can see easily how all the continents come back together. And about 250 million years ago, they were sort of all together, around that time frame, right?
Yep.
That's when they started cracking up. But before then, what happened? And what you did is you looked on the continents. And if you look at the colors, if everybody, when they're looking at that map there, look at the colors of what's on the continents. Those are geological signatures, correct?
That's correct. Yeah.
Now, if you look at those, and once you get back to when the crust all gets together, how do you go back in time from that? Well, you start looking at those and start basically, I guess, removing that. Is that what you did?
Yes, that's right. I'll just interject what you're saying there. This map came into being in 1990. It was only a couple of years prior to me starting my research. So I was very fortunate in getting this map, in particular having the continental geology completed at that time. So, and the difference between what the modeling technique that I've adopted to plate tectonics is that the plates, the remnant plates that make up these supercontinents in a plate tectonic perspective, they're random. So they're randomly moving and bang, wham, bang, crash, bang. Right. So you can't really, except for the bit that's joining one continent to the other, you can talk about the geology there, but it doesn't take into consideration the geology of the rest of the world, the continents in the rest of the world. Putting it together on a smaller radius allows you to see that the sedimentary basins, as I mentioned throughout my talk, form a network of basins, and these sedimentary basins, which are the shallow continental seas, and these surround the most ancient crusts, the pink and red and khaki coloured crusts. And I visualize those most ancient crusts. Just do away with the modern oceans now, and visualize the most ancient crusts as the ancient continents, and the network of sedimentary basins were the seas. So all I'm doing is putting back like we do with joining the continents together by removing the modern crusts, ocean crusts. We take away, in my continents, I'm taking away the ancient continental sea crusts and putting back together the most ancient crusts. You can just follow what I mean.
Yes.
The ancient crusts are equivalent on a par with the modern continent.
Okay. And you know what is really interesting when I watch those models? Antarctica didn't change in size. Everything else.
It recurves. It does change a little bit, but
yeah.
No,
but if you looked at, what was I wrong in seeing that?
No, that's
I mean, if you, what was really bizarre as I was watching the models go back, the certain Greenland and Antarctica seem to be the ones that were the most ancient and stayed around the longest.
That's correct. Whereas Australia, for example, and I'll show you here, this section here is that can you see that I'm highlighting with my cursor? That's the most ancient. Western Australia and northwestern Australia is the most ancient, whereas the eastern half are young. So by the time we get back to this most ancient crust that I'm talking about, Eastern Australia doesn't exist. Same with North America. The Canadian shield regions, I think you call them, and some of your Cordilleran region in Western America are the most ancient crusts, whereas the southwest region, and unfortunately your Florida too there, David, don't exist.
Yeah.
So they're the ones that those sediments are put back onto the ancient lands, the ancient exposed lands. It's when you erode these most ancient lands, the sediments have to go somewhere. And in my book, I do talk about you can calculate the surface area of these ancient crusts and times the average thickness of what's been eroded away, and you come to it's roughly equivalent to the surface area of the Paleozoic sedimentary basin. So there's justification in what I've done there, volume surface area wise.
No, it's totally amazing. It's really curious too. I'm going to ask a dumb question. This is a dumb question. I really think it is, but I'm going to ask it any. Oh yeah, this one's dumb, I think. Why would it be that those two, Greenland and Antarctica, which seem to be the most ancient and stay around the longest, those are the frozen continents now?
Yeah, they are.
That's coincidence, isn't it?
Yeah, bearing in mind that this is a published map, so I was not able to remove that white color in my models.
Oh, okay, I see.
So even though they're shown as white, they're not. That's not
Okay.
uh, ice. That's just the fact that the map itself is white.
Do we know what's
In,
underneath it? What kind of rocks are underneath it?
well, they're on a par with the pinks and reds and khakis that's shown there. They're all the way around the edge of almost a good deal of the edge of the Antarctic, for example, is exposed Archean and Proterozoic crusts. Same with Greenland. Around the margins is their ancient crusts. So you have to
Oh, okay,
make
I
a
gotcha.
judgment call
Okay.
there. Underneath the ice, it's
Oh, okay.
ancient.
So what you're saying is because you're again finding ancient crust all the way around
Yeah,
that you assume that it's got to be ancient
yeah.
crust in the
You
middle
have to make a
because
judgment call there. Yes,
okay, okay. So it is a
and
judgment call and in
and
the
it
future.
fitted well. So.
Okay. Yeah, but it is still absolutely
Mm.
mind-boggling that you did this part. I mean, you know, that was that's it took me years because I think people get so enamored by the idea that all the continents they know and love and see today, which are burned into our minds, right? If you show, the shape of Australia to most people who are, going to school, they all know what it is. So we literally
Yeah,
have these shapes burned into our brains. And so when you see them all fit together, 250 million years ago, I was so elated and amazed by that whole thing. Uh, I think when I first met you, I even asked you about that. I mean, what happens before that? And then you
mm.
come along with these models that actually model what probably happened by using geology in the same way. So if I understand you right, for those people who maybe didn't catch it, what you did is okay. You go back 250 million years ago, and now you have the today's continental plates. They're all together. To go before that, what you then do is you look at the most ancient parts of those continents, and then treat those as the ancient continents, which will then uh, sh- close up once again.
That's correct. Yeah.
Okay. Let's see. Do we have? Let's see if we have some questions. Let's go back up here. Um, just going to go flipping through them. Some things supported. Okay, I do have one question here. It's not really about the Earth, but it is a question. Dr. James Maxlow, what does you think about the presence of the moon? Moon helps maintain mountain ranges, stops them from sinking down. Okay, I'm not sure what that means, but maybe
No,
he's,
neither do I. I'm not going to answer it.
yeah, okay. When we don't know
I-
really,
I'm
maybe
sorry to
they can
say, but
clarify.
it's a nonsense question, really.
Okay, okay. So a question. Okay, I got you. Um, let's see what else. Antarctica seems most stable, perfect for a hiding place. Saying sequence. Okay. Anyways, well, if you have any questions, please put them in. We have them. I'm reading through them right now. I've got, of course, some other comments here. I got the green. Okay. One of my questions is when you get to, of course, the breaking up the continents. We're going to go before that, obviously. Before that, as you start assembling the more ancient crusts, ancient parts of the crust, where part of the continents we know aren't there anymore. Um, how do you go and find what would be shallow seas or water? Is that an easy task, or is that part of it, or is that something yet to be done?
It's a relative thing. In our geology mapping, for example, there's certain key indicators in the sediments that you map that indicate the depth of waters, the depth of the ancient sea. So when I say relatively shallow continental seas, it's relative to the depth of the modern oceans. The modern oceans are many parts of the oceans are very deep, of course, and the most ancient continental seas, by comparison, were not as deep as the modern oceans.
Okay. Let me put myself back up here. I'm just trying to play with the controls. Here's another question then on the water part. Obviously, water is coming through the crust. right?
Yep,
Water either leaches through through the rock itself, it's released, or it comes through the black smokers, I think what they're called or whatever.
that's correct. Yes.
What would you see as because that's a different process than really, or was it, than in the ancient times before the breakup of the crust, where it was smaller and crust was actually being formed. What was? Do you have an idea of how that water at that time would be produced?
Um, uh, it's much the same throughout history. During the early crustal forming process in the early Archaean, there's a lot of volcanic rocks involved in the crusts, and volcanic rocks have, as I indicated in the last podcast, I think it's about, I think from memory, about 15% by weight of volatiles, water and gases,
Mm-hmm. Mm-hmm.
retained in the crystal lattices of the volcanic material. And once that reaches surface, then that's devolatilized. So
Right.
it's expelled from the rocks themselves. And the black smoke is a classic example of this water and gases pouring out of the mantle region into this ocean and atmosphere. During the pre-breakup times, of course, the exposure of the volcanic rocks exposures were a lot less than what it is now, much less than what it is now. So therefore, the volume of the waters was much less than what it is now, steadily increasing over time because there has been volcanism all through time, but certainly by comparison, nowhere near as much as the volcanism in the oceans now. There's evidence um, going back to, I think, one of the oldest sedimentary rocks in the world was actually discovered by a professor at the Curtin University where I studied. And they're sedimentary rocks from a place here in WA. Was 3.91 billion years old. So there were sediments around and there was water around at that time. The oldest dated rocks on Earth are around about the 4 billion years old margin now. So whereas the moon rocks are about 4.54 billion years. There's about a 500 million year difference between the moon, age of the moon, and age of the Earth. And in my fourth podcast, I think I will bring that into it. Actually, it might be the next one, third one. I'll bring that aspect into it. I won't say much about it now, but I will bring that into it. The formation of the moon and Earth and its evolution in time.
Wow, that's pretty cool, man. You got some new work. I read on this stuff, and you're always ahead of me.
That's right.
Um, I'm supposed to know everything you know. That's my goal.
You're supposed to have
Another
read my
question.
book.
Yeah, I go through it. I go back to it. He goes, he said what there? Let me go back. What? Okay, let's on the same topic. What I mean, one of the things that our group talks about is, you're talking about the mechanism for mass increase, right? That is, subatomic particles come together, and you're saying in the D layer. And I think this is really interesting because people in our area, even like my father and I, who have a model of the universe, we have to be able to explain, can this happen? And of course, you can take subatomic particles and you can make an atom out of it. That in fact, I think astronomy talks about that in the middle of the sun, right? You get heavy elements. Now, in your opinion, because it's one thing to say there is so many percentages of gas, methane, and oxygen, etc., in rock that gets released, and that's where we get the waters. I mean, we people who think about the actual mass increase, that means water, methane, other things are being made. They're not, it's like
Manufactured in lower.
manufactured. Right.
That's right.
Okay, so that's one of the things you subscribe to, meaning that it's not only just like, oh, well, it's just like hydrogen because it's small, but actually larger atomic atoms of higher atomic counts get constructed, get made, and then get percolate themselves up to the surface and then eventually get released. So that of course resolves the problem with comets. But okay, so you're saying you think that's what's really happening.
That's correct. Yeah, that's correct. And bearing in mind the temperature and pressure conditions at that depth, of course, is beyond our wildest imagination. So just because we have solid rock here at surface, and that doesn't necessarily mean to say it's solid rock at the core mantle boundary. So it's only pure speculation of what that is. I can envisage it's something high end that we just can't comprehend at this stage. And then really it's the increase in volume, which is squeezing this newly formed material up to the surface. And of course, increase in volume means a stretching of the surface crust, stretching and cracking. So this material is being forced up along the mid-ocean ridge spreading centres all throughout the world. 80,000, I think it's 60,000 kilometres total length.
Right. Now, one of the things is the other thing that's really, truly astonishing when you really go back the way you have, which I think, again, you did enough work for at least 170 PhDs, in my opinion. If this was something that people were in universities doing, I mean, it would be so wonderful to see. I mean, there are just so many things that I won't get into it because I'm going to forget.
I'll just make a comment on that, David. As you mentioned in your introduction about difficulty in studying something like expansion tectonics at universities. And I was very lucky, and I went back as a mature age student, of course, and I was fortunate in that two of my supervisors actually had studied under Professor Sam Warren Carey from the University of Tasmania. So they were familiar with, then what was called expanding Earth theory then, and were very sympathetic and gave me a fairly liberal, free hand, and didn't really bother me. They just let me go. So I was fortunate that, and also my examiners, I was able to have some input in who examined both my theses, master's and PhD theses, and I got very high marks for those with these people because they were sympathetic to what I was doing and had some former training by Carey in this subject. And but to do it now, well, that's a different thing. And I'm not bragging here, but my PhD one, I got a commendation from the head honcho in Perth, Curtin University for this groundbreaking research. So I was very, very, along with your Lifetime Achievement award from the JPNC, this award was on my wall as well, and I take a lot of pride in it. But there's something else you mentioned about that too. I can't remember now. I'm having a senior's moment, so carry on.
No problem. It is fascinating, that side of it. I'm glad to hear that they sort of kept their hands off.
That's what you were saying, David.
Yeah.
Sorry, that was what I remember. What you were saying about enough context in my book to do 100 and so PhD theses, and you're absolutely right. And in fact, probably my master's thesis was involved in just getting the seafloor crusts modelled, and then from my PhD, I then did the continental crusts, and it really was post PhD work that I did on my own back that's added all this extra stuff with the paleomagnetics, climate, fossils, geography and space technology, etc., etc., etc. So I did meet I was approached by a young fellow quite a few years ago now who wanted to do a PhD on paleomagnetics to back up what I was doing. but unfortunately he redirected himself and went somewhere else. But yeah, each of those fields that I touch on in my book, there are multiple
They're
PhD.
immense. They're immense. I mean,
Because it's a whole different way of looking at
of
this
course.
information. It's a whole, as I said in my talk here, it's a whole new platform to
Well,
model it.
what I'm thinking, James, just this right off the top of my head right now, and I think this may be a strategy. This affects so many other fields that have nothing to do with people who care about plate tectonics or not. And I think people who are in the ancient world of looking at plants, the guy with the trees and stuff, have you found people like that who've embraced it, who don't have the problem of plate tectonics, or are they indoctrinated too and they just don't want to rock the boat on that?
They're very much indoctrinated into plate tectonics. There was a good example in Brisbane when I was living over there. We went to a dinosaur exhibition, and they had classic plate tectonic models of the crusts with their dinosaurs all plotted on these models and whatnot. And I turned around and said to one of the young fellows that was manning this particular booth, give me your address and I'll send you some real models. I was being probably very cheeky. And he just clammed up, said, like, that I'm not allowed to think the other way, you know. And yet, I think I mentioned the last talk, I knew a fellow from New Zealand, and he studied ammonites, and I mentioned the ammonites that he found in northern New Zealand, the North Island, New Zealand, only occurred in the North Island and in Mexico and Jurassic. And my Jurassic, the New Zealand, during the Jurassic times, New Zealand docked in against Mexico, and that curved around to the San Francisco area, Los Angeles area, New Caledonia tagging on there, and that sandwich between there and Brisbane in Queensland. So things like that, you know, here's two areas in the world that only have these particular fossils, and lo and behold, on expansion tectonics. David Knoll, the nut and fruit tree fellow from here in Perth, WA, he has something like 80,000 fruit and nut tree locations, ancient fossils and and modern examples plotted throughout the world. And he independently came up with expanding Earth, as he called it, because there was multiple occasions where examples of, say, palm trees on one side of the Pacific Ocean only occur on the other side, in one place on the other side. And when you join these together, bingo, they all come together. And he actually got me to do a talk at one of his conferences one time, and I was able to show and animate a selection of his work there on my models, and bingo, there it was. You know, too easy.
Yeah. So you think he subscribes to that then?
Oh yes, absolutely. He's a good friend of mine,
And so there's an end, right? And these things, what's going to happen is the way all these things work is you just got to keep. It's like networking, right? One person sees it and goes, "Wow, I can explain this," and the person goes, "Wow, you can," and the person looks at it, and there's going to be enough people who will look for truth. Because if it works, it puts together, it has a basis for it, then these people are going to say, well, this is, whether or not you agree with this or not, I do. It explains everything. And with eventually the attrition moves, and it moves, I think eventually it's going to move from discipline to discipline. And so eventually what will happen is those people who are still holding on to it, doesn't matter, because the three people next to them are all excited about how this explains and makes things much more clear to them. And they're already working on it, and they're plotting things, and, that's sort of the way it shifts in almost any. It's a social shift. It's not even a scientific.
One of the fields that I'm really keen to get somebody involved in, the dinosaurs in Western North America the classic areas in the western region there. And we have in inland Queensland, we have classic dinosaur regions. And when my models come back, they come back together, they join like that, go that way. So North America and Australia, and here's fossils there, here they go there, bingo. Whereas in plate tectonics, you have Panthalassa Ocean, much bigger than the Pacific Ocean, separating these two major dinosaur fields in two separate countries. And of course, the only explanation is that these dinosaurs migrated down across the South Pole and then up South America and up into North America, or the other way around, whichever way you want to go. And it just doesn't happen. So land bridges join the continents together like I've done, and there's an instant land bridge.
Yeah, it's just amazing. To me, it's just the opportunities there and what we can do there. I mean, to me as a software engineer, I'm just thinking making a software program that could be a worldwide sort of an open source software program where people could take it and plot anything they want on it by, going on, clicking and plotting the things and then labeling it and allow people to layer these things. It would be an immense tool that I think would be absolutely used by millions of scientists.
That's already available for fossil data.
Right, but it's a fixed radius, right?
Yeah,
you can't like say what this would be is you would dial it 50 million years ago, put your data there, and then other people would put their data there, and as you dialed it, you could see the things change. Imagine the different patterns and things you would see. You would get explanations for dinosaur, even their roaming, of how things affected, all kinds of things that paleontologists
I've introduced in my website. I do have some data modeling there, and John Eichler has done a brilliant job at setting it up for me, and it does show exactly what we're talking about now, but in a static model way rather than a spherical modeling.
Okay, I've got somebody down in our green room, as I call it, and wants to come on air and talk to you. So you never know. I think I know this person, so it shouldn't be. It's not a surprise. But I'm going to bring it. This is Toby. Toby, are you there? Can you unmute? You've got to unmute yourself. There you go, Toby.
Can you hear me?
Yes, I can.
Yes.
Okay, good. If I drop out, I'll get my mic on. I'm just using the external mic right now. So my question is, what differentiates the various elements as mass accumulates in the core or whatever mechanism as this energy, as this mass is accumulated in the Earth from what you would say the sun being influenced by the sun, correct?
Well, it's pure speculation, of course.
Right.
What people don't appreciate is that the volcanic rocks that make up the seafloor crusts is exposed mantle. They're not continental crusts per se. They're just simply cooled and quenched mantle rocks. So we have exposed mantle. So what we're seeing at surface is the basaltic rocks plus the volatiles and water expelled. As you go deeper down, those basaltic rocks change to higher grade rocks. I can't remember the eclogites and various other fancy rocks, but once you get beyond the, say, middle to lower crustal regions, then it becomes speculative as to how the differentiation occurs at the lower mantle region. Having said that, if you differentiate what we call the mafic rocks, the basalts, etc., mafic as in magnesium iron rich rocks, as distinct from felsic, which is felspar and silica rich rocks, you can differentiate the mafic rocks by simply expelling the mafic portion of it, and what's left behind is the more silica and alkali-rich rocks, which form your granites. So at your near crust and near surface, you can differentiate this material into basaltic rocks right through into granitic rocks from the same melt. But what happens in the core mantle, I'm not a physicist, so I can't really answer that from a technical point of view.
Okay, yeah. What I was envisioning was as the mass accumulates and the ratio of the elements remains the same, but now you have more iron or more carbon or more silver or gold than you did at the beginning. Would you say that would be correct?
I'm not convinced it's actually in elemental form. As intimated before, the temperature and pressure conditions at the core mantle boundary, I don't know, you'd probably have to study the conditions in the sun, for example, to understand the elements in that, what happens at the surface of the sun there. I can visualize it being similar but not quite the same as that. But what I'm saying is the extreme temperatures and extreme pressures at that region, I'm not convinced that you have pure element, pure gold, silver, iron, nickel, etc., etc. It's only when you start getting away from that these maybe condense. I don't think condense is the correct word, but condense, synthesize into specific elements and compounds to form our rocks that we're more familiar with.
Sure, I see a tie-in with low energy nuclear change physics that's related to cold fusion at those temperatures and pressures. There could be formations of these elements due to forces involved, and somehow the ratios of those elements must do with the geometry of the sphere. Yeah, okay, thank you for your answer.
You're welcome. We've lost you, David.
I got to get myself unmuted myself too.
Yeah, that's
I mean, well, thank you. It's like we're the blind leading the blind. Yeah, that's why people come and subscribe to my channel, because I don't know how to unmute myself. So, but anyways, it's interesting. I remember 10 years ago, or I can't remember how many years anymore, James. But you came to me saying, "Hey, we've got mass evidence of mass increase. Help us." And I think one of the things that even in Neil Adams' video, he says it, and he says it correctly. He says, this changes everything. This doesn't change just geology. It changes particle physics. It changes our understanding of the way we have to look. This can give us clues as to what atomic structure is. Toby was right. What ratios are these things being made? How are they being made? Now, and that's one of the things that, if once this is accepted, those questions are going to have to be answered, and that's going to push other sciences forward. I think that's just one of the things that people are missing out. And one of the ways I get people into what I call dissident science, where, because our group is known for, showing Einstein wrong, the Big Bang wrong, relativity wrong, all those things. Because if people look at these things, just like you look at geology, and you come with an open mind. Okay, I'm going to look at relativity. And so you look at the logic. You don't have your reputation on it. You don't have your, the food coming on your table based on it. You have a free and open mind. And when you go and you look at those things and you come to these conclusions, then you're saying, oh my gosh, this changes everything. When you look at particle physics, and you really do, and I have for many years via a lot of great people, I would say we're lucky if we can keep anything past 1930. After that, if you look at the methodology, if you read Unziker's book on how they do engineering, you're a geologist. My father's an engineer. I come from it. If you look at the engineering decisions that he reveals in the Higgs fake about how they go about finding particles, you would be fired on the first day if you're an engineer. Because it's just like academia. Well, they filter this out. Wait, why you that noise is important? No, we're going to filter that out because we're trying to get to this Higgs particle, and if you leave this in, we can't get there.
That's a good point there, David. And I haven't mentioned space geodetics at all in any of, well, and I won't in any of the talks, but it's interesting when the space technology measuring the dimension of the Earth and the movements of the plates on Earth, when that technology, there was enough receiver stations spread throughout the world, etc. And by about the early 90s, they were able to access the accumulated data from, I think, 1976 right up to about 91 in order to calculate the network, close the global network of all these stations. And what they found was there was a net increase in Earth radius of 18 millimeters per year, plus or minus a number of millimeters for errors, and which is on a par with the 22 millimeters per year, which I've calculated using surface areas. But geodetics, geodetics is essentially a glorified survey, global survey. And I used to work as a surveyor in my younger days. And if you do go out on a farm or a property or something like that, and you do a traverse around the property, you will always, there will always be a small error when you close off at the end of your survey. And it's you then tweak your measurements to make sure that closes. So you're closing off errors, and that over the next couple of years, these from 18 millimeters, these geodetic people gradually for a start they assumed that they adopted that as being an error. So there was 18 millimeters in error. So they then tweaked the mathematics to remove that error. Like all good surveyors, they need to remove that error. So what you just said a moment ago, hey, hang on a bit, that 18 millimeters is real, it should be there. So, but they've adopted this fixed radius Earth, the quantifying plate tectonics, of course. So they've mathematically and statistically removed this 18 millimeters, and now they're down to something like 0.1 or 0.2 of a millimeter increase per year. And I met one of the senior geotechnicians at Sicily, at the conference, Expanding Earth conference in Sicily. And we encouraged him to, and they used to filter the data. They actually removed, I think it was about 60% of the data, global data, because this data wasn't behaving itself to come up with this 0.1, 0.2 millimeter error. Anyway, we encouraged him to run the total data set without removing anything, and it upped it to about 0.3 of a millimeter or something else. But we couldn't convince him that to backtrack on the mathematics to 1991 era and rerun it for that. They were insistent that their math is correct. So, yeah, we'll just have to wait.
It's funny. There's a parallel in GPS. I don't know. You may have come across the name Ron Hatch, who was in his 80s. He just died last year, but he was a longtime member of our organization, the MPA and the CMPs. He had over 30 patents in GPS. So you're talking to somebody who knows GPS really well. In fact, he had a small company which was bought out by Deere Tractor, and his job that he was a millionaire. He didn't have to work anymore, but he decided, well, I said, why are you working? He goes, they gave me an offer for a salary I couldn't refuse. So you're talking about, we're not talking about Joe Schmo, right? We're talking about one of the top minds in GPS on the planet. Well, he wrote a book about how GPS doesn't support Einstein's relativity. In fact, it shows its errors. And one of the things that he was working on just before he passed away, and I was talking with him a lot. It was very similar to what you're talking about. NASA had a real problem where they couldn't find, this is how small, listen to this number, 0.56 picoseconds. A picosecond is an incredibly short amount of time. But when you're talking about GPS and you're trying to drive a tractor on a field within a centimeter of distance correctly so you can make the most out of your production of not running over, that's what his job was. It makes a huge difference. Well, it turned out that he was convinced, at least in the end, I don't think, and he wrote back to them. He says, look, I think I know what's going on here. And what he was saying is that when you take into account the movement of the satellite and the speed of light, if you add the movement of the satellite to the speed of light, the error goes away. Now, that 1.56 feet, that is a bomb. It's a nuclear bomb to relativity. Why? Nothing can go faster than the speed of light. But what he did, he calculated that if you added the velocity of the GPS satellite, and then on the way back you subtracted it, that you didn't have that error anymore. So you're talking about an immensely small error that is astronomically important. And like I said, atomic bomb. This means, like, guess what, folks? You can go faster speed of light. That the speed of light is not constant, as Einstein said. But they don't want to say it. They don't want to be the ones to reveal that. He said that when he gave those talks about how relativity wasn't used, and people in GPS, they know it. I've heard people. Greg Bulk, who is of the CMPs, he said he was sitting next to somebody during one of Ron Hatch's talks of another person in GPS. And so here's a guy making a living in GPS. He's sitting in the audience listening to Ron Hatch next to my friend Greg Bulk. He turns to Greg Bulk and says, guess what? It's a little dirty secret, but we don't use GPS. Yet last year I sat at a high school, listened to Bill Nye, the science guy, who my daughter and everybody others kids grew up with, pulls out his cell phone and says, if it wasn't for relativity, we wouldn't know where we were on the planet. So what we have is people repeating and repeating and repeating these things, and their reputations are on the line, and they don't want to be the ones to upset the apple cart. And so you have evidence everywhere for these small things that do matter. The changes. That was one of the things I was talking with Ron Hatch about, exactly what you were talking about, geodetic, where they can. I saw there's a map of the world I've seen with arrows on it, vectors, and those vectors tell you the movement that they're measuring. And if you look at that, your first conclusion goes, if you really look at these, the Earth would be expanding.
That's right.
Because if you look at all the arrows just with your visualization, you're going, my conclusion is that, yeah, there's movement, but this movement can't be all in this direction because it's moving away, and the only way you can explain those arrows, just the direction of the arrows, is the Earth's expanding. You're familiar with that map then?
Oh yes. I've got a copy in my book as a
right.
Yeah.
Yeah, so I mean that's very much what's going on in the world, and let's see. Let me see if we have any. What is it? We're talking about. People. One of the problems is we have people who are new to all of this, so they this is the problem with what you're doing, James. It touches too much of science. I mean, you come here and talk about. Probably, an amazing talk about reconstructing even beyond what the average person who accepts. There's quite a lot of people now. I would not be lying if I didn't think that tens of thousands of people now subscribe to expansion tectonics, maybe even more. I mean, I really believe it inside their head. I remember a good story, James, that this is 10 years back. I work in computer science, and my fellow scientists, and they're interesting people. A lot of them. This guy was from Russia, and there's a lot of great Russian scientists, a lot of really great Russian scientists. So we were talking one day, and he goes, "What are you always doing? What is this?" Because people find out about your hobbies. So I was, talking about it. I said, "Yeah, well, this thing." And he says, "Oh, you want to hear?" So he says, "Einstein's wrong, Big Bang's wrong." He goes, "I've been thinking that doesn't blow my mind." And then I talked about expansion tectonics. And then I started talking with him, and he just, his mind was blown. And I started giving him a reason. And he goes, "Ah, oh, all right, Dave, that's right. Okay." So we go home. The next day, come in, and I'm sitting at my cubicle programming, right? This guy comes up and taps me on the shoulder. And he goes, "David, I hate you." And I go, "Why do you hate me?" And he goes like, "I can't get it out of my brain. Expansion tectonics. I can't get it out of brain. It makes sense. I can't stop thinking about it." The next thing I know, he throws about 20 questions at me. And I think what's going to eventually happen is that people more and more who see it, I mean, my gosh, he at that time that was before a lot of your books and stuff. At that time, he went and saw Neil Adams, and once he saw that, he understood. But I mean, I think what's going to happen is Neil Adams' videos have millions of views,
Mm.
right? And those things get into people's brains, and the general public are way ahead a lot of times of of people.
I've had a lot to do with Neil. We do disagreement on a lot of
Of
things, but
course, sure,
um,
sure,
and basically our modelling back to 200 million years, closing off the
right,
ocean, freezing principle, exactly the same. And the
right,
other person is Klaus Vogel, the late Klaus Vogel. Uh,
right,
his his models are identical to my models as
sure, of
well.
course, yeah,
The three of it, so there's three models essentially identical, taking back and closing off the continents. But
right,
I'm the only one, because I'm a
right,
geologist, I'm the only one that's capable of doing the continental cross. And I couldn't convince Neil to merge our
right.
modelling techniques in particular, because
He's yeah,
he's a graphic person. He's brilliant.
sure,
He has
sure,
and he has a graphics team there, but I couldn't convince him to merge our
yeah.
two things together. But it was unfortunate, but not no.
Yeah, I wish he would. I mean, that would be great. I mean, he's a stubborn guy. I mean, let's
He
face
is
it.
stubborn,
Yeah,
and he
but
gets
he
on the
but
wrong side of people like geologists
yeah,
in some
I
of the
know.
stuff.
I know. It's but you know what I think the way I look at it is I wouldn't even be sitting here with you if it wasn't for what he did.
Yeah,
And one of the things is we have to understand, and even you, this would be an interesting question for you because you are I mean the one of the most important, if not maybe the most important geologist of the 20th century, not including yourself now, but of the 20th century, Samuel Warren Carey handed you in 1994, basically handed the mantle over to the expansion, it was expansion tectonics to you. And I am sure there are things that even Carey looked at and other people before you who you might admire and you stand on their shoulders. I know my father and I, we have our model of the universe. We are standing on shoulders of people that we took we couldn't exist. Our model couldn't exist. I couldn't. It couldn't exist without Borchert's work, without Unel Deneu's work, without New. But then there are other things that those people who you are standing on their shoulders, you disagree with certain things. And even though
it's just
Adams
it was
brings a lot of people,
unfortunate.
you do that.
Yeah,
Yeah,
yeah. Carey was 50 years ahead of his time. It was just
for sure.
unfortunate that he was well and truly retired by the time I came on the scene. And while he I sent him a copy of my master's thesis to him, and he that's when he decided to pass on his baton to me to take over. But unfortunately, he passed away in 2002, and that's when I finished my PhD thesis. So yeah, he was well and truly ahead of his time, and it's just unfortunate because he and I could have worked extremely well
Oh
together.
yeah,
Yeah.
yeah, yeah. But I mean, there are other people too, though, that you look at. I know, again, if we go look at my father and I have a model. We're standing on people's shoulders that we
Mm.
use their ideas, but they didn't go as far. And in this case, they're still alive, but they have different ideas. But that's the way science works. And with Carey, I think it's a little different. It's unfortunate. It was just a generational thing, right? I mean, he was pretty old when he died. He was in his 90s, wasn't he?
Oh yes. Oh yes.
Yeah,
Yeah.
yeah. So I mean, it wasn't that he died young because of his lifestyle or something. He had quite a long career, But it's we have to understand that as much as people who accept certain things, Glenn Borker, he's a geologist. He's told me many times, and he's the one who wrote, in my opinion, he's one of the greatest philosophers and scientific philosophers of our time. Infinity is just an incredible concept that he's brought to science, especially physics. But he makes a living with subduction. And he gets paid very well. And
You need to read my book then, because I do.
Yeah,
stuff.
I know, but he knows all about it. But for his career, he can't. He's not going to be coming out like that because, he even though he's retired, and he's told me, he says, "Look, Dave, there's a lot of evidence for expansion tectonics, but publicly, no one's going to hire him if he is get associated." And that's sad because in reality, if he knew more about it, he may be giving better answers for his clients. But the climate doesn't allow that. Isn't that bizarre?
There's an interesting question from Scotty there. Isn't gravity working against the expansion?
Which one is that?
I think it's fairly early, just after Toby.
Is that in the? It may be in the private chat. Is that in the private chat?
Yeah.
Okay, what's the question?
Is gravity working against the expansion?
I think I have that somewhere. Yeah. Go ahead.
Well, it's not. Gravity is interesting in that because mass is increasing, gravity is increasing as well. And it was during the Permian 250 million years ago, when the Earth was half the size of what it is now, the surface gravity was half, 50% of what it is now. And Stephen Hurrell, in his work on gravity and dinosaurs, he came up with exactly the same figure, and he was working on his dinosaur models at the same time I was working on my small Earth models, and also working through the mathematics of all these, the mechanics of all this, and we came up with the same answer. And and gravity worked against the dinosaurs, and by the time you get up to the end of the Cretaceous, 66 million years ago, the gravity was around about 65-70% of what it is now. I think the size of the dinosaurs basically decreased with time, and that's possibly an overriding factor as well. So it certainly went against them, but it's certainly not working against expansion. It's just, it is changing and it is increasing, but it's from the dinosaurs, as I mentioned, it's working quite well with fitting in the dinosaur.
Yeah, in fact, that's one of the things is, I don't know who came up with that first that term, but paleogravity, right? That's if you go to a university and say, hey, could you point me to your paleogravity specialists? I don't think they exist, do they?
They're part of geophysics.
But the reason you would study it would because it would change. Why would anybody care? Right. The evidence, I guess the only evidence I remember talking with Stephen, one of the interesting evidences they have geologically in ancient geological terms were the slope of sand dunes.
Sand dunes. I put him onto that. Yeah.
Yeah. There you go. Of course. But why don't you explain, because people are curious a lot. Again, I know all your stuff. I forget there's a lot of this is new. Explain to someone how you can find the slope of sand dunes in the past and how that relates to the gravitational field.
Well, loose sand will form a slope, and that's called the natural angle of repose, and that currently is 40 degrees. 40 degrees from the horizontal. The dip of that slope is around about the 40-degree mark. Different if you have different coarse angular grains versus rounded grains, the angle will be slightly different, but roughly 40 degrees. And you can actually measure these, what do they call them? Just trying to think what the term is for. Yeah, anyway, the bedding. It's a form of bedding back in the ancient times, and I don't know the difference, but Stephen managed to find some, and there is a difference. So in theory, if you have a lower gravity, then you can have a steeper angle. Whereas if you have a higher gravity, that angle will flatten down to a lower slope.
So basically, if you stack, a bunch of little teeny rocks on top of each other, and then let the friction, let them settle in because of their own friction and because of gravity.
The back end of a sand dune, a wind-blown sand dune, for example, is roughly 40 degrees slope.
Okay, 40 degrees. So how would you get those? I mean, how would you get a slope in ancient rock? How would that show up?
So, there's dune sands and there's deltas as well. The foreslope and the front of the deltas, they give a characteristic slope as well as it's rilling down the slope as the sediments are being flushed in, like the Nile River or your Mississippi River. They have deltas at the front, and the front of those they will just cascade down the front, and that gives a characteristic slope. I'm just thinking of a classic cliff face in the north and here in WA, which exposes these. So you have angular beds coming down like that, and then horizontal beds with angle. Get an angle there. Right. I'll go the other one. It's opposite of what I do. Oh, yeah, there you go. So you got these are your beds accumulating. It's opposite to what the screen is. The beds are accumulating in time at that angle, and then you have a shift in your water, your river flow and what coming in and your data, and you get a flat horizontal layer of sediments on top of that. So that will give you an indication.
I get it. That's interesting. I was wondering how that
angle there, and this particular outcrop it's Silurian that I'm thinking about shows exactly that. So that they do occur. They're not common, but they do occur.
Wow. I mean, that's what would be, again, this is just another thing. I mean, you could have people getting their PhDs in gravity.
That's
right. I mean, going and looking for evidence. There's got to be lots of other evidence, not just the dinosaurs, and just the mechanic. Yeah, go ahead.
That's right. The thing you have to they have to overcome this mental image that gravity remains constant at the time. But you have to remove that. It's like removing increasing Earth radius. If you accept it, yes, why not? And accept gravity changing, why not? And then you can go out and research this and find all these things that will support your little theory. But if you put those blinkers on and go as you well know.
Yeah. And for everybody who doesn't know, I think WA, what you talk about, is Western Australia, right?
It's not Washington.
Well, no, we have people from all around the world. Actually, Farouk, who's a good young mind, he's from Morocco watching. So, what was I going to say? Oh, darn it. I had another story about, oh, well, slipped my mind because I thinking of too many things. But let's see. I think another thing that people are talking about in the chat, which we talked about last time you were on, was a lot about the progression of the Earth. Oh, that's a good one to talk about. Not only did you go beyond the crustal expansion, which other people did before you, obviously, you were not the first person to put those crusts together to form a ball. You met one of the pioneers, Otto. Was it Otto?
Klaus Vogel.
Yeah, right. And so you did that, but then you went beyond that, and that's what you talked about today, which was going beforehand, before the crustal breakup, and realizing let's take the ancient
Mm.
rock and make that the new crust to be broken up, and you did that, which was absolutely fantastic. Which is at least 3 dozen. I would give that a 3 dozen PhD work
Yeah,
there. So I'm going to start putting like numbers on how many PhDs that should have been. You also went 5 million years into the future, and
that's
all you
right.
are showing us is that it's going to cost us more energy and money to get to places because it continues to expand. Where do you see most of the expansion when you showed that model? Maybe could you bring that up? Maybe on there. I think that would be interesting because one of the
Uh,
things it's like, oh, the future.
I'd have to run. I'd have to run the animation through. So it's,
Yeah, but
uh,
yeah, but I think you have your slides there. I still have them available. So if you could move to the slide where you have the future one, and we can watch it. There's no problem. I can watch those all day. You guys, people, if you're new to this, just
it's that
go
one.
and watch these animations. So let me add this to the stream here. This one here.
Mm.
But I can watch these all day. Let's just talk about a little bit. You notice again, look at the size of Antarctica and look at the size of Greenland, right? They're
That
huge.
yellow circle is the radius of
Current Earth
current.
or the Earth.
Yeah,
And so these are places that only you, as a modeler of small models, Earths, you're the only person who's ever done this, right?
that's correct. Yeah, I'm probably the only person that can do it.
Yeah. Well, we're going to
It's
hopefully
impossibly
change
hard.
that.
Yeah,
You're gonna eat healthy. You're not gonna do anything like go, skydiving or anything, James. I'm gonna get you on a whole plant-based diet like me because we need you to be around a long time. So when you teach these courses and we get young minds interested, that you can be not the only person that does this. That's the idea, right?
I've still got these models in my shed in the
Yeah.
backyard. And
Yeah.
unfortunately, the colours are starting to fade now. So
Yeah, we're going to
uh,
have to work on that. So tell
yeah,
us, yeah. So again, what you're doing here is we're still now are we now there's a crust is breaking up, right? That's
that's
what's
right.
already started.
So, yeah.
So we're in the later, yeah,
To answer your question, for
future.
moving to the future, um, the Los Angeles, what's that? The Mexican Gulf there. What's that Gulf called?
That's the Baja, California.
Baja, yeah.
Yeah, Baja.
Uh, and the San Andreas Fault goes
Right,
through that joint, isn't
right,
it? So,
right.
so by 5 years, million years into the future, I think that actually separates. So that peninsula becomes
So it's
a
true that people who
uh,
like Superman in the movie Superman, he bought up all Lex Luthor bought up all the property along the Andreas Fault because he's going to accelerate that breakup by putting bombs there and then making it happen. That's not going to happen. But here we go. This is close to this. This
yeah,
is
two
present
more.
day.
Next one.
Present day is recent, and then the next one will be 5 million years into the future.
That's right. So
And you got to pick the color. What color did you choose?
it's a purpley color.
Okay, there's a purpley
So
color.
this region here, at the top end of the Red Sea, that that rifts apart. So we'll do away with the Suez Canal, and that's a connection, a seaway connection through there. The New Zealand, I think, is influenced a little bit, and where everywhere there's earthquake activity now, that's where your major uh, um, shift in the plates is occurring. Really, that's people. Plate tectonics says that's a collisional. The earthquakes are a collisional occurrence, but really in plate expansion tectonics, it's actually a brittle fracturing. So it's actually
Right.
separating apart. So the crust is cracking and breaking up and moving, jostling as well. So that San Andreas Fault, for example, that will eventually break through there, and that peninsula will be an island. But
Right.
you'll have to hang around for 5 million years, though.
Right. Yeah. So you're telling us the future.
That's
So
right.
in 5 million years, if the human race is still alive, that's a big problem. Of course, we don't
I'm
know that
surprised your
answer.
bridge is still standing, though. That's your San Francisco bridge. Is that one? Is it?
Yeah,
So,
yeah. I suppose supposedly they supposedly took care of that, but we'll find out, I'm sure. So this is interesting. This comment here: dinosaurs lived in a more buoyant atmosphere. Now, this is really, in my opinion, because we don't accept expansion tectonics and movement of, I mean, the change of gravity, right? I think they're trying. This sort of, to me, represents people who are recognizing that physically in our gravity today, dinosaurs, if they were born to the size, they would be blobs and they would die in a few minutes because
that's
they
right.
can't survive the mechanics of them that cannot survive. And you have people like Stephen Hurl who study this. But I think this idea of a more buoyant atmosphere really comes from the idea that, well, we do know that the mechanical part of dinosaurs are hard to explain. So let's try to come up with an explanation other than gravity changes. So
That's right.
is that the way you read this kind of
Well,
comment?
there is some merit in it because you have a lower gravity. The moisture in the atmosphere will stay in the atmosphere a lot longer than what it does. So it will be a thicker atmosphere. I can visualize it being a thicker, moisture atmosphere.
Right.
But I'll just leave the screen a moment and grab this book.
No problem.
This book.
Okay.
This
Oh no,
book
no.
is a
Who wrote that one?
This
I
is
don't have
by
that.
Brian Ford. He's a English
Stephen
professor.
Hurl. He didn't tell me about this because this is his
No, you
competition.
need to read
No.
this book, guys. You need to read this book. See how he's got that. He modelled that dinosaur. It's actually
Right.
that this is actually water. They're actually
Oh.
they're
Oh,
actually
that's
walking on
right.
water.
That's that they were really aquatic animals.
He puts a really good case to explain why they've got long necks and long tails, etc. So they're actually aquatic. Most of them are aquatic beasts, rather than the Jurassic Park type theme where they're stomping around fields and whatnot. And it's only what was I going to say? Yeah, so they have the long legs and long necks, so they can reach down and graze on the bottom of the lakes and near shores of the seas and whatnot. And the demise of the dinosaurs, the end Cretaceous extinction, was not an asteroid or meteorite or anything like that. It was actually when Australia and Antarctica parted company and initiated the Southern Ocean as that started to separate and form the Southern Ocean. There was a change in sea levels, and the change in sea levels was manifested in your Western Interior Seaway, and that drained. So that was where all your Western North America dinosaurs were, in this Western Interior Seaway. And when Australia and Antarctica separated over a period of about 8 to 10 years, your waters, your sea levels went down, and withdrew these waters out of this Western Interior Seaway, hence your demise of your dinosaurs. And not only there, elsewhere in the world as well. So it's just, this will be a focus on my next talk, actually, extinction events, which actually probably the fourth talk rather. I'll bring in the extinction events, and these extinction events match exactly where with these the end Cretaceous extinction is when Antarctica and Australia separated, parted company and separated. The end Triassic event was when North America and Australia parted company, and the North and South Pacific Oceans merged to be one open. Prior to that, there were two separate oceans. And Permian extinction event, the major one, was when the continental crusts started to break up and formed the modern ocean. So each of these, there's five main extinction events. They coincide with these major changes in sea level by
Right.
breaking up with these continents and whatnot. And so when you put everything together in an expansion tectonic framework, all
Right.
these things come together.
Yeah.
And
Yeah.
and I think the title of my next talk is fact or mere coincidence. So you've got to
Right.
think: is this mere coincidence or is it fact? And yes, and that's the question I pose. All these coincidences come together, and oh, jingoes, they make sense, sort of thing. Rather than having a random and catastrophic attitude to all these
Right.
things,
Right.
ad hoc theory to these events, you do away with these and they all fit together precisely. It's
Yeah.
predictable and
Yeah.
understandable.
Life is pretty resilient, and if you have an asteroid come along, yeah, it may wipe a lot of things out, but it grows back pretty quickly. This is just to go back to a comment we already said. It is a more recent comment, so maybe I use. So Earth liquid water and water trapped in rocks has remained the same. No new water made or lost. I think you've already answered that, which would be you think that it's actually being made along with.
That's right. The black smoke is evidence that it's being made. It's constantly being new water is constantly being made and added to the volume of the oceans.
And that's
And
from
as these mid-ocean ridge lines extend over time, as the surface area, radius and surface area increases, the length of these mid-ocean ridges increase. So your volume, your new water coming in increases.
Right, but I think the question is really, is the water there or has always been there, or
No.
no? So part of the mass increase is water.
Your new matter is being formed.
Right.
At
Matter. Right.
your mantle. So there's your new.
Right.
The new molecules and particles that form your water and rocks and gases and so on. As that's being as your mantle increases in volume, and that's forcing this material up to the surface, that's when your new rocks and your new gases and water come to surface. So it's not that it was always constant. It's because the mass of the Earth is increasing, mass and size of the Earth is increasing in time. So therefore, your volume of these lesser elements are increasing as well.
Right. And this is along the same lines. As the Earth's mass and gravity increase, what will happen to our mountains? And will life forms eventually be smaller and smaller? I think Stephen Hurl addresses that second part, right? He
right.
has, was it him that made, or it may have been someone else but I saw the diagram, the famous diagram of all the biggest animals, basically, of that time. Was that Stephen Hurl's work?
Yes, it was. Yeah.
Okay, yeah, and basically, if those who haven't seen it, look up Stephen Hurl, get his book, or go to his website, dinox.org, and you can see basically he just plotted the biggest animals, land animals, not aquatic, but land animals, and you can see a definite decline in the size. So that I think that's going to be true. As for the mountains, that's a good question because mountains are formed in expanding Earth, not by collisions, but by buckling, uncurving, correct?
That's roughly correct. Yes.
Right.
And
Now,
and
so
and
in the
your
future,
topography. So
well,
your
in the
mountains
future,
themselves,
yeah,
what you see as mountains really is the end product of erosion. So you just have to elevate these
okay,
the continents and whatnot, and you get erosion. That's where you get your fabulous mountainscapes, and that's from erosion. What people don't appreciate is that those mountains are not pushed up; their whole mass is elevated. And as I explained in my
okay. So
previous,
how's that elevation happen for those people who maybe say it again?
So we'll start off. Here's as the radius of the Earth increases, the surface curvature flattens.
Right.
By my hand, so you have a tighter curvature way back in, say, the Permian, and now it's flatter. So there's a I can't remember the term. There's a residual because of the rigidity of the crust, the outer margins of the continents will remain depressed. So as it's trying to flatten, because of the rigidity, there's a residual component of there. So and then all your erosion is in here, in your high parts of the central parts of the continents. Once that erodes away, that weakens, that thins that region, weakens it, and then you get that. And all those sediments, of course, are washed down here and accumulate along your margins. There's your sea level here, for example. So all your sediments are down here on your continental shelf. And then once that continental crust fails and it starts to flatten out, then that's lifted up. The outer margins is lifted up. So you actually get Cliff Ollier from here in WA. There's a lot of famous people in WA. He's studied the mountain ranges all over the world. He's a professor of geography. And these mountain ranges are actually not formed by a collision, they're formed by elevation. And they're actually plateaus. And
but does he believe that? Because he's not a Spanish tectonicist, is he?
Yes, he is. Yes, he is.
Oh, he is?
Yeah.
Oh, okay.
He's a great mate of mine. But anyway, what I'm saying is you got these plateaus. Now these are exposed to erosion, and then you get all the drainage, and that's where your topography comes into it. So
as that happens more and more, will they get higher, or
they get flatter and flatter, and over time your erosion will eventually erode those down to.
So what you're saying is, according to expansion tectonics, the major upheavals have been really fulfilled.
No, I won't say that, because most of the upheaval throughout the world now has actually occurred in the past 2 million years. Modern continents, the past 2 million years, and this is what is in Cliff Ollier's book.
Oh, yes, of course, yeah, Cliff Ollier.
And
he's expansionist. Yeah.
Can't remember the name of his book anyway. But yeah, so these mountain ranges, and they always, like the Appalachians and the Cordilleras and our Great Dividing Range here in Australia, Eastern Australia, all parallel the coast. They all and equivalents on the Europe and Africa and whatnot. They're all around the margins of the continents rather than interior.
Right.
The most ancient ones are internal, like our Arunta complex in central Australia and various others that I won't mention. They're the equivalent of the outer margins of the modern continents. They're equivalent to the outer margins of the most ancient continents when we're back to the Archaean, Proterozoic Archaean, when we had the continental seas. So yeah, there'll still be a flattening of the continental crust. There'll still be a continual elevation of those outer margins, or continual elevation and counterbuckling. So yeah, so as the erosion comes down, erodes them, it'll still be coming up again, but probably nowhere near as dramatic as what they are at the moment, because a lot of that initial elevation and whatnot occurred just prior to breakup of the crusts during the late Permian.
Right. Okay. All right. Here's another question. Antarctica ice sheet formation 40 million years ago. What happened 65 million years ago?
I will actually mention that in my fourth talk. I'll show that, exactly that.
Okay. Well, that's a good teaser.
What people need to appreciate is Antarctica is only in the past 40 million years has Antarctica been on the South Pole, within the South Polar region. Prior to that, it actually straddled the equator. That's why you get fossils of ferns and things in Antarctica.
Yeah, the paleontologists chalk that up to climate changing, right? They don't, it's like, I don't, that would be, if you really think about it, even that idea, let's say everything was on a fixed radius still, and we have a tropics down at the pole.
By definition, the polar region is cold.
Right. And so or you'd have to have a temper for that to be a tropical. The rest would have to be a blazing inferno where no
Extremely.
one could live. They don't, they just don't put those ideas together like Pangea. Literally, if you put Pangea, all the land on one side of the Earth's rotation is going to cause just by physics another island on the other side because of the water will be displaced. So it doesn't work. You put it on a model right now, it will fail, but somehow that doesn't.
So getting back to this question,
Yes.
around the 40 million years ago time, that's when I can't work it. No, forget it. That's when Antarctica first migrated.
Right.
It's the South Pole.
Right.
So here's Antarctica from the equator, migrating South Pole, migrating down
Right.
onto the South Pole.
Right.
Follow that?
Yep.
40 million years ago, that outer edge just started to move into the South Polar region. And over that 40 million years, it's the continents, Antarctica has migrated onto and well into the South Polar region. So that's when it's actually 33 million years ago, but that's when the ice sheets started to develop on Antarctica, permanent ice sheets to what they are now. So when our climate people talk about melting of the ice sheets, melting of the Antarctica ice sheet, really, well, bear in mind, back to what I said, you got the Antarctica migrating across. Once it moves beyond that again, then you start to start to melt that side and accumulate more ice on the other side. If I can get all that together. But yeah, and I'll show you that on one of my slides in the next couple of talks. As that migrates across onto it, the ice sheet builds up, but as it moves away, it starts to melt again on the receding end, on the advancing end rather. On the advancing end, as it leaves the North Polar ice cap, it moves, and that's when you get the ice melting. But bearing in mind, the South Polar ice cap is land-based. It's on Antarctica. It's continental ice, whereas the Arctic is a marine ice shelf, and that's susceptible to the temperature of the currents and climate more so than the Antarctica. Antarctica, the sea ice around Antarctica, that's where you get changes over time with the changing temperatures of the ocean waters.
Right. And we're going to be wrapping up now because we're past our 2 hours here. But it was actually the pole location that finally flipped you from a regular geologist to expansion tectonics, wasn't it? Right?
I'm not sure what you're coming at.
Okay. What I'm saying is
my
that when
laterite,
I asked you what was the reason you went from just regular geology to believing that expansion tectonics really was the correct model, you told me it was when you mapped out the South Pole. That's what you told me 10 years ago.
That added to it, yeah. Really,
Yeah.
Really, it was when I was working in the Pilbara region of West Australia in the late 70s, early 70s, sorry. I was working there, and the Pilbara region is about 300 by 500 kilometres or something, and it's a huge big dome, preserved dome, and it's Archaean. But all the way around the edges, they're dipping like this.
Right.
So these are the rocks are dipping like this, whereas the surface curvature is like this. And in the central part of the Pilbara, 30 kilometres of sediments and volcanic rocks have been eroded to expose the basement rocks. And I put it all together, and I thought, this could be a remnant of an ancient Earth, showing me just a remnant with the dipping of the outer crust. And that worked. That's where I started from, and that's where started thinking along those lines, that this was a remnant of this most ancient crust, and it's worked out that it is. That's exactly what it is.
Right.
But try to tell any other geologist, you get a different answer.
Yeah. All right. Well, listen, thank you so much again for this talk. It's always great. I'm really surprised because we've talked about the subject for many decades actually in our group, but there's so many new people that they haven't heard about it. And even some of our oldsters were not aware of it. And I think that's really great. And so I do appreciate it. And we'll be getting a next talk from you in the coming weeks. There's two more coming up, so everybody
Correct.
can stay tuned for that. But thank you so much for presenting today.
You're most welcome. Thank you, Ron. Good night,
Okay.
all.
Good night. Yes, it is late in Australia right now where he is. It's past midnight, so I really want to thank him once again, and I want to thank all of you who've been subscribing to my channel, Dissident Science. Also, those who have subscribed to the YouTube channel for the CNPS. And we'll be having more of these talks coming up. If you know of somebody or a subject, or you yourself want to present to us, you think you've been working on some things that outside of mainstream science that people really need to know, get in contact with me. You can just go to our website, and we have a couple of websites that you can go to. Here they are. Oh, those are the YouTube channels where you're watching now. But if you go to any of these websites and take a look, you can send me an email, and we can get you on the air. Again, we have a format of where you can talk anywhere from as little as you want to an hour. Usually a half an hour is a good half an hour to an hour, and then we have an hour worth of discussion. So again, I want to thank everybody for their support, and I'm going to take you out with some videos. Actually, I had a video for today. I'm going to show them to you in the end. So if you stick around, James, you'll like this one. I was supposed to play it right in the beginning, but I didn't. I'll have it next time. It's all new stuff. So we're going to see a couple videos right now. They're called stingers. Enjoy. So there you go. That was supposed to be in the beginning. It goes, what kind of host am I? I even make these videos. I'm going to make another one. I promise you. And remember, it says, hey, Dave. Next time we talk, James, just say, hey, Dave, play that stinger. It looks pretty cool. But I'm going to play you one more that I made also for the CMPS, who is one of the sponsors for this. And again, I encourage you to join the organization to support people thinking outside of the box, like Dr. James Maxlow. There's so many other fields where people are not afraid of the truth. And I want to thank everybody and all the members of the CMPS and their memberships, annual memberships, which help pay for channels like this. And I'm going to play you a little stinger for the CMPS. Pretty cool. Now I'm not hearing. I didn't hear any audio. I don't know if people heard audio with that. They're supposed to. They actually have a soundtrack for that. But again, thanks so much, and I appreciate it. We'll be back next week. You can go to our website, naturalphilosophy.org, and you can subscribe, or you can just go to these channels and subscribe to our CMPS YouTube channel and my Dissident Science YouTube channel, and you will be alerted when we put these out, because usually in the beginning of the week we'll have our subject and the person who's talking, and we'll have those. So if you are subscribed, you will be alerted to it. And before we start, if you go to YouTube and subscribe, that will send you a notification on your telephone, because most people are watching on their telephones these days, and you will know when we go to air. So thank you very much. And again, I'm David D. Hilstner. I am your science therapist trying to get you to become a critical thinker. Ciao for now.